Yair Minsky, who's going to talk about Weil-Petersson geometry, then filling and prime structures.
Thank you very much. Thank you for the invitation to the organizer. It's been really a great conference so far. Although I was thinking coming up the stairs, I really enjoyed the 4 talks so far, and I was really tired. And I thought, one more talk, well, at least I can maybe sleep in the back. Anyway, it turns out, so you guys should do what you need to do. Okay, so, so this talk is, let me just sort of start with the motivation for this talk. So, what's the setup? You have, surprisingly, a pseudo-Anosov polymorphism on the surface of genus G. I think this works for punctures, but stick with the closed case. And the question that comes up often is the study of the dilatation of these things. You look at the, say, dt of f is the translation distance in the Teichmüller space, so the theorem of d of x, f of x for x in the Teichmüller space, s, where this is Teichmüller distance. Well, we're going to, as you might guess, we're going to go away from Teichmüller distance in a few minutes, but I want to start with the motivation. So, so Penner in the 80s showed. So the question is, how small can this get? Okay, and for any given surface, there's some lower bound on how small this dilatation can get. And Penner showed that there's no lower bound as the genus grows, and in fact, there are examples where so the minimum of dt of f as for a given s is less than some constant over the genus of s, or the Euler characteristic of s. So it actually shrinks. The distance shrinks as the genus grows. So maybe if you haven't seen this picture before, you should. This is what Saul calls the alien phone dial. So have all the younger people, do they know what a phone dial is?
They're near the typewriters.
So the basic deal is you look at, you do something kind of complicated in a little piece of this, a bounded piece of this. Maybe you do some twisting, so here, here, and here, or something. You do a little something that's complicated, let's call that phi, and then you rotate by one click. So maybe R1 just moves everything one handle over, and so after G clicks, you get back to the beginning, and you get back to the complicated part again. So the rate of growth of the length of anything, take a curve, it gets a little longer, and then it runs around kind of by rotations, and then it gets a little longer again. So the rate of growth, the exponential rate of growth, is 1 over g times some constant, right? So that's where this comes from. So you get much slower growth if you have such a thing. And in a beautiful theorem of Farb-Leininger-Margalit, they studied what happens in general. They kind of asked the natural question of, can we explain all such short dilatations? If you fix a C and look at all pairs Fs with this bound, how can you understand them all? Where do they come from? And the answer was they come from a finite number of 3 manifolds. So maybe we can say it this way. If you look at the set of all, maybe let me write over here for a second. If I have a pair Fs, pseudo-Anosov on a surface S, I can produce the, call it MFS is the mapping torus. So it's a 3 manifold. We're going to look at that 3 manifold a lot today. And so they prove the following, that the set of all F, so if you fix C, then the set of all pairs Fs such that the Teichmüller dilatation of F is less than or equal to that constant over G, that set is obtained from finitely many cusp 3 manifolds. So in the following sense, So how do I get a three manifold? So which finitely many three manifolds do you get? You look at MFS, and then you puncture it. So we'll put a little circle there to puncture it. This is MFS minus the singular orbits of the pseudo-Anosov. So if you realize the pseudo-Anosov on the surface with its usual picture with the quadratic differential, it has these singular points, and then when you take the three manifold, the mapping torus that goes around, these points travel around in loops, maybe more than once. So there's a finite number of singular loops. If you delete them from the manifold, you get a manifold with cusps, or a manifold whose compact core has torus boundary components, and that's this thing. And so there's finitely many of these. Okay, that's the point. So this is a finite set. Maybe we'll call it sort of M sub C. Okay, that's the theorem. So somehow these infinitely many of very high, arbitrarily high genus examples all live in a finite number of three manifolds. And if you haven't seen this picture before, it's worth kind of thinking about it a little bit. The picture kind of looks like this. Let me draw that three manifold again. So maybe here's one vibration, and then let me draw one singular orbit just to have around. And then what does another vibration look like in the same manifold? Well, imagine you look at this plane field associated to the vibration, and change the direction of all the plane fields in some way, like this. If you do it the right way, and this is, I guess, the existence of this phenomenon in general is, we should mention Fried and Thurston, who studied this phenomenon in the, I guess, late 70s. You can do this in such a way that you get a new foliation whose leaves are still compact but very, very large, and so a typical, so you get some kind of a this is hard to draw. So here's like here's a little bit of it, and it kind of goes around and around and around. So if you kind of follow it around this manifold, it takes. Now I'm drawing it as if it's one-dimensional, but this is meant to be a surface. So there's a fiber of some other vibration might run around nearly parallel to these fibers, but takes much longer to close up. So it has a very, very large genus. That's the picture. The flow around the manifold, the same flow as we had for the first vibration, now has very short return time. And so you expect its dilatation, its Teichmüller dilatation, to be small, and that's exactly what you see. You see that it looks like a constant over the genus, if you use at least for some of these. Okay, so that's the picture. Now, the last thing to say about this, which is worth saying for this talk, is what's the difference between the MFS and so there could be infinitely many of these that give rise to the same drilled manifold. What's that all about? So it's the following phenomenon. If you thicken up this missing curve a little bit, you get a solid torus, and the original fiber cuts this torus in a meridian disk that looks like that. That was the original picture. The green fiber may also cut this. Now the inside is gone, right? And so we have a torus boundary. The green fiber cuts this torus boundary in a circle, which is not the same circle. In fact, it might wind around many, many times, as you depending on which fiber you chose. And so you get a very, very long, complicated curve as your new meridian. And when you fill that meridian in, you get the new fibered closed three manifold. So infinitely many meridian curves might show up as surgery coefficients that get you back from this finite set of manifolds to this possibly infinite set of manifolds. Okay, so that's the picture in the setting of Teichmüller dilatation. Okay.
Do we know that the set of M sub FS's that are not eroded, do we know that that's infinite enough?
We don't, I guess. No, I guess for sufficiently high C, you do not. But I guess for sufficiently low C, it's empty. So there's a transition. Okay, so what are we going to do with this in this talk? How long do I have? Am I almost done? So the question is, what happens in the base? So that's the question I want to talk about today. what about the Weil-Petersson translation distance of f? Can that be small? And so on. And I think I'm going to once again not give the definition of the Weil-Petersson metric, because I'm not going to use the definition of the Weil-Petersson metric. I'm just going to use theorems about it. But the Weil-Petersson, I mean, we've heard about it this week. It's a different metric on the Teichmüller space. Maybe the one important thing to say about the definition of the Weil-Petersson metric is that Weil-Petersson is defined in terms of an L2 metric on the cotangent space of the Teichmüller space, the cotangent space of the Teichmüller space, and therefore the dual L2 metric on the tangent space. So it's an integral of, so there's a tensor, you integrate the square of the tensor, and you get the norm squared. Whereas the Teichmüller metric is defined in terms of an L1 metric on the cotangent of the Teichmüller space. And therefore, as soon as the words L1 and L2 show up, you immediately should relate them to each other, and you should apply the Cauchy-Schwarz inequality. I was telling Chris the other day that I think every time I use Cauchy-Schwarz, it's like rolling a die. Like, is it going to work against me or for me? I don't know. But this time, what it gives you is that the Weil-Petersson dilatation of f is bounded by what turns out to be the square root of the area of the surface. So just put it like this, times the Teichmüller. So, which means that if I, so this is like the square root of the genus. I'm not going to make a big fuss over genus versus other characteristic. So what we are bounding over here is the Teichmüller dilatation times genus. It's bounded by constant. So we can think of that as a kind of normalization of the Teichmüller metric suited to this question. And so what we have to normalize by for this is the square root of the genus. So we have the square root of the genus times the Weil-Petersson dilatation is bounded by roughly the genus of times the Teichmüller dilatation. So if this is less than a constant, then so is this. So all of the examples for this inequality, for G d Teich, are also examples for the square root of G times the Weil-Petersson. So that's somehow, that tells us what question to ask. We should think about this quantity. When is this quantity bounded? Okay, so that's the first point. But the second point is that there's more. There are more examples where you can bound the Weil-Petersson dilatation where the Teichmüller dilatation is not bounded. And the reason is that Dehn twists are cheap in the Weil-Petersson metric. You can, this is a Theorem of Wolpert and Chu, that the Teichmüller space with the Weil-Petersson metric is incomplete, and the way in which it's incomplete is that you can pinch curves to length 0 in finite distance. So you can go from a surface like this, pick your favorite curve, and apply a deformation to it, which gets you to the noded. You sort of draw it like this. You get the noded one where the length is 0. This is finite in the Weil-Petersson metric. And once you get, and that's one observation from here. And then once you get near this point where you've pinched it to 0 length, Dehn twists become as cheap as you want. So that means, so you can twist arbitrarily many times for kind of bounded, for finite price. So in fact, I guess there was, right, we saw this picture on the board earlier this week, right? And the kind of model for the Weil-Petersson metric looks sort of like this. Well, in dimension 2 it looks like this, and for higher genus it's this, it contains this as sort of cross sections. But what I'm doing is, since this is a finite distance away, I can go really close and then do a whole lot of Dehn twist and come back, and I've done the Dehn twist for kind of arbitrarily many Dehn twists for finite distance, which means, for example, if you fix f, pseudo-Anosov, and then maybe tau is a Dehn twist around some curve, then dwp of f out of the n is bounded for some constant for all n. Okay? And I guess you might ask, is this even pseudo-Anosov? Well, it's pseudo-Anosov for all that finitely many n. So eventually it's pseudo-Anosov, and it is bounded. Peterson translation distance. So if I'm going to, well, I haven't yet put in the square root of g. So if this is for a fixed g. Okay, for a fixed g, I can add as many Dehn twists as I want, and it doesn't cost me more than a constant. So so I have to fold that into my picture here. Okay. So what do I have to allow in order for this to happen? What happens to mf? M. So now I fix an f, but I look at mf tau to the n. Yes. So in this case, so this is an infinite collection of manifolds. How are they related to each other? They're just related to each other by, there's some manifold in which I've removed the curve associated to tau, and I've cut it out, and then I've re-glued it with a Dehn twist. So they're the same up to Dehn filling, up to Dehn surgery of the cusp manifold where I've removed alpha. So I'm going to, in this, I should really define M circle F tau n s to be M F. What am I saying? Sorry. Minus this curve alpha. Say, let's write alpha cross some, say 0 in whatever coordinate system I have. Okay, so take a level curve, a closed, simple level curve, and delete it, and you get a cusp through manifold. And the punchline of this example is that while there's infinitely many of these, there's only one of these. Okay, so what I should somehow be looking for a theorem that says that if I bound this renormalized, wherever it went, the renormalized Weil-Petersson distance, I should expect to see finitely many three manifolds after I've taken care of both phenomena, the drilling along these sort of curves and drilling along the horizontal curves. And that's the theorem. So, right here maybe, theorem.
Sorry, so the m dot that you have used, is that the same?
No,
Not
this is
the
a
same
new
notation.
This is a new circle, same notation for a new object. Yeah. So should I put a little WP here?
Okay.
Yeah. From now on, yeah. So I want to redefine my operation. So so let me say it this way. So this let's see. The set of pairs Fs, so that dWP, I guess it's right, the same sort of, is bound by C over the square root of G. Okay, that's the same inequality, is obtained from finitely many cusp 3 manifolds by deletion, sort of, let's see, after deletion or of vertical, let's just write it this way, vertical and horizontal curves. So one has to be a little bit careful. What do I mean by vertical and horizontal curves? So vertical means transverse to the vibration. So that's what we had in the beginning. And horizontal means lying in a fiber. So what I would see here, there might be a vertical curve that I have to remove. Maybe it goes around several times, and maybe a collection of kind of sort of unknotted curves, like a bunch of simple curves on different level surfaces. Okay, so that's the picture you should expect in general. Finally many such pictures. So there's a little bit of a ambiguity about what this means, because when I say lying in a fiber, which fiber do I mean? Of course, I guess for each Fs, there's the fiber associated to S, and they should lie in that fiber. But after I delete them, they live in some fixed 3 manifold, and that manifold somehow, I guess what I want to say is they kind of simultaneously lie in all the fibers that I might get when I fiber.
So you
When I
can't
fill
really
in.
go around them. You cannot twist around the curve that goes around.
You mean can these sort of braid around?
Yeah, don't twist around.
Well, I only drew one, but yeah, I mean, yes. So actually, this is a good point what you're saying. So first of all, there are several curves, and you should not forget that there's a pseudo-Anosov here. There's a monodromy, so something actually complicated is happening anyway. But I did leave something out in this statement. There are two things kind of left unsaid by this theorem. One is that over here, I deleted not just an arbitrary transverse curve, but a curve which is the singular orbit. And I did not give that statement here because we don't think it's true in general. So there are examples where the things that come up do have the vertical curves that are not orbits of the singular point. They're a little floppier than that. And we don't quite have a complete picture of when that does and doesn't happen. So that's one point. So let me say,
So there actually are examples.
So there are examples where in the following sense. So what we actually prove is a theorem about 3 manifolds, not a theorem about Weil-Petersson geometry. The examples that we have, certainly, they come up in the proof as kind of sequences of Serger's 3 manifolds. We haven't computed their Weil-Petersson dilatation. We have, so the Weil-Petersson, I'll write in a minute, the Weil-Petersson controls the 3 manifold, but not the other direction. So, right, Sam, do we know that the floppy examples come up with controlled Weil-Petersson? We don't, right? Yeah. Yeah. But I sort of expect it. So 2 points, okay, so let me just, so that's point 1. So the vertical curves, let me write it as a question since I admitted we don't know the answer. Are vertical curves singular orbits? And the second question is, can we really get the twisting going to infinity, genus going to infinity, and normalized, and the normalized Weil-Petersson dilatation bounded. So in the example of the twisting that I gave over here, I kept the genus fixed and I did a lot of twisting. Okay? So the picture that we have here suggests that there should be examples in which the twisting goes to infinity and the genus goes to infinity. And we have heuristic reasons for thinking this is actually what happens, but it's actually, I'm afraid one might have to use the definition of the Weil-Petersson metric. Okay, so
can I ask you, what's happening for the monodromy around the horizontally removed curves? What's happening?
you mean on the torus boundaries, or
Yeah.
sorry, on the horizontal curve? So the monodromy is changing by Dehn twists. That's more or less what it has to be.
Okay.
If they're staying in the fibers, then
Okay.
yeah. Okay, so that's what we want to talk about. So how do we convert this statement into a statement about 3 manifolds? So there's so this theorem. Let's see. So this theorem is work of several people, but so Schlenker, Kojima-McShane, Brock-Bromberg. I think that the statement I'm going to use is going to it appears in the work of Brock and Bromberg, but the techniques kind of are done by all of these people. So what's the theorem relates Weil-Petersson distance to volume, and so it says that the volume of the hyperbolic manifold M Fs is bounded above. There's a number here which I'm going to write constant times square root of g. Yeah, times d WP. So this normalized Weil-Petersson dilatation bounds the volume of the hyperbolic structure on free manifold. So this is a strengthening of a theorem by Jeff Brock for a more early theorem of Jeff Brock, in which there were inequalities in both directions, but the constants weren't known. And so the interesting new thing is that constants are known to depend on, to be in fact the square root of the genus. So that means if we can bound this quantity, then we can bound this quantity. So the set of all, so this immediately implies that the set of all manifolds that occur in our question, they all have bounded volume, right? If this is bounded, then they have bounded volume. And so we can apply a theorem further back in time, I guess Jorgensen and Thurston. So the set, so the set manifolds, say three manifolds, whose volume, so hyperbolic three manifolds, whose volume is less than a given V, is obtained from a finite collection of cusped three manifolds by Dehn. Okay? This is, so we start with this condition, we get a bound on the volume, and then we use Jorgensen-Thurston to restrict ourselves to a finite collection of cusped three manifolds. So that's it. Except that you have to now resolve the following question. So now, how many ways can cusped three manifolds give rise to fiber three manifolds? That's the question we now have to ask, right? So, so I have finitely many of these, and presumably do infinitely many different Dehn fillings on them, and everything I get by this infinite list are all fibered. And so it had better be true that I need to somehow control what these look like, which cusp manifolds actually show up in this picture. So, and after a little bit of bookkeeping, it reduces to the following question. I could just think about one. So let M. Actually, let me do this on a new board. Okay. Okay, so let M, the circle, be cusp three manifold, cusp, and I guess hyperbolic. Three manifold. And now suppose I have an infinite, so suppose Mi is an infinite, well, it's a list of I, are all fibered. So these, sorry, let me say this. They're all Dehn fillings of M, such that two things. One is each Mi fibers. So I guess we write Mi fibers over the circle, and the fiber Si. And two, the coefficients go to infinity. So the meridian coefficients go to infinity on every cusp. Okay, so that's the setting that we're in. So I want to, now from this I need to show that M circle is a fibered, so is equal to a fibered three manifold minus horizontal and vertical curves. Okay, and the logic, I mean, anyway, if you work a little bit with three manifolds, you are sure that this is true, because anything more complicated is going to generate crap. It's not going to be able to fiber. That's the proof. Okay, so that's the deal. Showing this fact is the point. Okay, so let's do a warm up.
So how, in this remark 2, how big is the Teichmüller dilatation?
Say again.
For the guys where the twisting goes to infinity.
What happens to Teichmüller dilatation?
It goes to infinity also, or?
It has to go to infinity because these twists, if the horizontal curves are there, then yeah, it goes to infinity. Because if it didn't, you wouldn't have those horizontal curves by so. Okay. Okay, so let's do a warm up case. Well, the warm-up is a theorem of Tall. Which says the following: if let me say it this way. For every genus G that exists in epsilon, such that if n is homomorphic to the surface of genus G cross R and it's hyperbolic, so if I have a hyperbolic structure of infinite volume on S cross R, and I look at the curves of length less than E, so the curves gamma of length of gamma, these are geodesics. Let's take geodesics of length less than E, epsilon, sorry, are formed, let me write that in, unlinked collection of level curves. Which is to say, up to isotopy, you can draw your manifold exactly the way I wanted to before. You have a surface cross R with some hyperbolic metric on it, and then the curves of length less than epsilon are in fact simple curves. They all lie on level surfaces inside this. There could be infinitely many of them because this is an infinite volume manifold, but they have to live on this kind of family of level surfaces up to isotopy. So they have exactly the shape of the horizontal curves we were hoping to find. Okay? So, right, so this is a theorem of Tall. The proof, I should say, uses the fact that you can fill this manifold with pleated surfaces, which are a nicely controlled family of almost hyperbolic surfaces, and you can control the way that they penetrate the Margulis tubes of these short curves, and then you apply work of Friedman, Haas, and Scott, I guess, to replace immersed surfaces by embedded surfaces. With a certain amount of care, you can find these embedded level surfaces which pass through each of the curves. So it's a kind of delicate theorem, but that's what we have. And so, how does that apply to our setting? So, so in our setting, if we knew that the genus of the SIs, if this was bounded, which is obviously not what we know, but if it was bounded, we'd be done, because now we would have a bunch of, we just apply Tall's theorem to the infinite cyclic cover of MI. Right? MI is fibered. The genus of the fiber is fixed or bounded, and so its infinite cyclic cover looks like one of these. All the curves in the Dehn filling, all the Dehn filling curves have to be very short when I goes to infinity, right? So this is the way Dehn filling works, and this is part of the Jorgensen-Thurston theorem. The way this goes is that the manifolds you get from the cusp manifolds by Dehn surgery with very high coefficient has very, very short geodesics in those solid tori. And so we are immediately exactly in this setting of the theorem of Tall, and we look at that infinite cyclic cover, and all those curves must be short, so they all must be level curves in this structure. And then you have to do a tiny bit of, you have to check that when you take the quotient, nothing funky happens. Like in fact, you can still fiber the quotient with the same kind of surfaces that you had. That's a little check. So that's the end of the story when the genus is bounded, but obviously we're interested in the case when it's not bounded. So let me try to tell you a little bit about that. Also note that in that case, in the case where the genus was bounded, we didn't get any vertical curves actually, like this, right? I mean, the Tall's theorem just kind of only produced horizontal curves. There were no vertical curves. So that's also an indication that we're not really a full story. Okay, so what do we do in general? In general, so we need some sort of finite thing in our manifold, in our mother manifold, M circle, that will control this infinite process. And so let me write another theorem. Since I've been a little trip through the 70s and 80s. So, here's a theorem in the 80s. Floyd and Hotel. I think 81. Let me try to state it kind of more or less the way they did. Let M, well, give the same name, be a Haken. We don't really need to say Haken because we have boundary, but Haken three-manifold. It's oriented. No, I don't remember. This is the educational part of the talk. Oh yeah, sorry. Haken three-manifold with incompressible boundary. That's all we need. Okay. Then there exists a finite collection, say B1 through Bn. What are these? These are properly embedded branched surfaces. And they are, sorry, well, I think they call these incompressible branch surfaces, so let me put that in here, sorry. Put it over here. So they're incompressible, I have to tell you more about them. And boundary incompressible, so I owe you some definitions, such that every incompressible, boundary incompressible, properly embedded surface in M circle is carried on one with positive weights. So these are the finite list of objects which will help us control all of our infinitely many fibers that we had. So some definitions. So what's an incompressible surface? I think everybody probably knows what an incompressible surface is. It's just, well, it's a surface that does not have any compression. It's a compression, here's a surface. Compression is a curve on the surface that bounds a disk in a three-manifold, right? So you don't allow these. In boundary incompressible, doesn't allow, so these surfaces are allowed to be properly embedded, which means if you draw the boundary, here's the boundary of the three-manifold, that what you are not allowed to have is a little local picture that looks like this. So here's the surface. It hits the three-manifold in its boundary, and then it comes out into the interior, and this is not allowed. So here's a little piece of the surface, and inside it there's the following kind of half compressing disk. Okay, see this horizontal disk in my picture? It's like, that's called a boundary compression, and that's not allowed. Yeah, where did the boundary come from? So I was talking about cusped manifolds the whole time, but I really want to think about manifolds with torus boundaries, because, and in what's missing is a solid torus inside. So is that okay? So boundary. So M circle is a compact manifold with boundary. I didn't say compact. All right, so that's what boundary incompressibility is. What is a branch surface?
Can I just ask, why did you write Hawk in there? I mean, if they do have boundary,
Yeah, I wrote Hawking for educational reasons. Right. So they proved their theorem for closed manifolds without boundary as well, and then you have to say Hawking. But our manifolds are automatically Hawking. Okay, so what's a branch surface? A branch surface is a surface with branches. So it looks the local. So it's too complex. It's like a train track for three manifolds, right? That's exactly how it was conceived and why it exists. But look, here's the local picture. Here's a little piece of surface, and then here's the branching locus. Well, part of it looks like this. Regarding a couple pictures. So here's a little bit of branching, okay? But in 3 dimensions, the branching locus might cross itself. So here's another piece of branching down here, maybe. Okay, so you see these. Right, there's one sheet coming down here. There's a sheet in the middle, and there's a sheet coming up from below, and then the branch locus meets in a little point. And that's a generic picture. You could so a generic branch surface looks like this. Except that along the boundary, so if I draw the boundary of M, then I will see it might intersect the boundary in a train track, and then you can sort of have this thing coming out like that. So this is how it meets the boundary in the train track. This is the boundary of the branch surface in the boundary of the three manifold is a train track. Okay, that's a branch surface kind of in general. There's one more thing to say about this, which is it's very helpful to thicken it a little bit and try to study what the thickened structure looks like. So a regular neighborhood, N of B, looks like this. Let's see if I can do this. So let's try to draw this a little more rectangularly. So here's the first two sheets look like this. Drawn. And then the other one comes in like this. Okay, so there's one kind of slot coming on the left, one slot coming in from the front, and did I do that wrong?
It's the bottom. The bottom right needs a...
This?
Yeah.
Oh shoot, let's see.
You want to get it hidden. You want it to be hidden.
Yeah, no, here it's not. Well,
Yeah,
okay.
right there.
Mine's a little wiggly. Yeah, okay.
That stops.
Right? So there's. Man. Come up here. Okay, so there's like a slot coming on the left, there's a slot coming on the front.
And the other one, yeah,
This is much easier to draw on the paper. Okay, so there's the picture. There's a kind of vertical foliation here, which we'll call I. It's the foliation by intervals. I'm doing this so I can give you a little notation because we still have 5 minutes, right?
Yeah.
So does that continue? 5 minutes?
We'll see.
Yeah. All right. Yeah. So all right. So let me try to say this. So we have this picture, and what does it mean for the surfaces to be carried by this thing? Though they have to be isotopic into the middle of this neighborhood so that they travel through it, kind of transverse to the interval. This runs through here. Maybe another one runs through there, and another one runs through here. Okay, and so just like for curves on train tracks, except in 3 dimensions, and at least for me, this whole project actually has been about learning why you can't just say it's just like train tracks. It's actually like that. It's actually delicate to actually make anything work. And there's other, maybe, so, yeah, I think I'm going to run out of time. So let me try to very quickly say what happens. Actually, the other thing to say is I drew the picture in the interior, and one should also draw it along the boundary, where it's thickening of this, and one should think about that. So, okay. Oh, and I have to say maybe a couple more things here. So there's the boundary of the neighborhood divided into two parts, the horizontal part and the vertical part. And here, the horizontal part are the flat pieces you see here, and the one on top and so on. The vertical part is the part that's foliated by the leaves, and that's like this vertical rectangle here and this vertical rectangle over there. So the vertical part is a bunch of rectangles and annuli, and the horizontal part is somehow the direction along which the surfaces are running. Okay, so that's names. So how are we going to do this? Let me say a few words about what we do. So we need to use this theorem, so we have to start with a bunch of surfaces. So this is what we do. We take, so inside Mi, remember we have Si, which lives inside Mi. Mi, it's the filling of M circle, so we can think of this as M circle union a bunch of solid tori. So these are the solid tori that I've added to M circle to get Mi is fibered, and now I'm going to choose Si to intersect the Vi minimally. Okay, so it's some surface, and the cores of the Vi are some collection of curves, and this is an isotopy class. I can move it around, so I choose the representative of the isotopy class of the fiber, so it intersects Vi as few times as possible. And then, why do I do this? Now I form Si circle, which lives inside M circle. It's just, in fact, the intersection of M circle of Si. Right, so this is Si intersect M circle. I cut it by the solid tori. Now it's a surface with boundary, and this is now an incompressible boundary incompressible surface. And the boundary incompressibility, it comes from this minimality. Okay, so this is, if you like exercises like this, you can see how, if you ever had this picture where this is the boundary of one of the tori, in our surface Si, you could reduce the number of intersections with the solid surface. So those can't exist, so it's boundary incompressible. So I have the whole picture. So now let B be a Floyd-Ortel branch surface. Since I ran out of time, I didn't tell you all the properties that the branch surface has, and I'm not going to, I guess. But there's kind of a list of roughly 3 properties that make a branch surface, where it is, the condition of being incompressible for a branch surface is a little list of conditions, which I'm not going to write down now. But we have these conditions. And now we have to study what happens. And maybe, let me try to, I don't know how fast to say this. So what are we going to do? We have, so the picture looks roughly like this. Let me now draw a cartoon of what's going on. Here's the little neighborhood of the branch surface. And here's my Si that's running through. It's running through a bunch of times. So that's Si circle. And I know that the manifold is fibered. So maybe kind of without being too careful about the picture, there's kind of, there are 2 parts of this picture. Maybe, well, one more thing. I can move this Si, I can thicken it a little bit, and then push it around so that it exactly meets the horizontal boundary whenever possible. I mean, so that kind of push it up against the horizontal boundary in this direction, and down against the horizontal boundary in this direction. Maybe there are several pieces of it here. So here's a more typical part of how I did this. I eat up the horizontal boundary using the thickened fiber. Okay, so now I have this red region is a kind of thin product region around the fiber, and the complement is what I want to study. So what happens in the complement? So I look at Mi minus let's call this regular neighborhood T sub I minus T sub I. Well, the manifold is fibered. So this is also an SI cross 0, 1. Right? This was a regular neighborhood of SI, so it's an SI cross 0, 1. I cut it out of a fibered manifold. What's left is still a product. So the region over here is a product. And I want to understand what it looks like. And here's a cartoon of what it looks like for the last minute. So here is this region. So there's red, it was cut out by the red surfaces, so like this, and then it's a product in here. And I see in here two kinds of regions. I see the complement of the regular neighborhood, so Mi minus the regular neighborhood, and then I see the regular neighborhood, what's left of it, so after I cut out the red. What's left of the regular neighborhood after I cut out the red is a bunch of foliated pieces. So these pieces are foliated, and these pieces are not. And so the last thing I need to do is to prove that I can actually extend this foliation to the whole thing. So in other words, the goal, maybe this is where I'll be. The goal is to show that if you look at Mi minus the regular neighborhood, I guess what I'm removing, I didn't say what to do about the solid tori. So I cheated in this. But I take the regular neighborhood of the branch surface, and I also take the solid tori away. Sorry, this is not quite right. VIB. These are the solid tori. I'm cheating you that meet the branch surface. So there are some solid tori. The picture looks like this. Here is the solid tori. Here's the branch surface in our 3 manifold. It meets the solid tori. This is the cartoon. And then there's this kind of complementary region, which is what I'm trying to understand. Inside it are other solid tori that, for all I know, are knotted in some complicated way. And I have to understand this region. And then I fill them in, right? So I know the whole thing is a product. And so the last thing is to show that this thing is a product already. So in other words, this kind of mysterious region in the middle of my product region is a product. And I'll leave you with 2 more pictures. What can go wrong? I have a surface cross I. I have a bunch of foliated things in it. And I want their complement to be foliated, be a product. So 2 things can go wrong. One is the foliated region could be knotted. So I have some foliated by interval region, and maybe it's somehow knotted inside here. Okay? And I also, it could be, I didn't really draw, I drew you just a tiny local picture. Maybe the foliated region looks like this. Maybe it runs from the same side of the product to itself. And if either of these things happen, then the complement is not a product. Okay, so I have to rule out each of them, and this one I rule out with geometry, and this one I rule out by minimizing complexity in a different way than I've sort of said. But I think I'm out of time, so I'll stop there.
Is there a relationship between the SI and the B that's the surface that this is carried on with positive weights? Like, what's the relationship there? So you took an SI,
I took an SI.
and then you say let B be the surface.
The surface, sorry, that carries SI. Sorry.
Right.
Not any branch surface. So there's an infinite number of SIs that show up, and there's only finally going to be branch surfaces that Floyd will give me that carry all of them. So I picked the one that carries SI. So what I'm really doing is, there are infinitely many things, and finally many branch surfaces. I can restrict to one of the branch surfaces and all of the SIs that it carries, and look at that sequence, that subsequence. Yeah.
What do you mean you rule out the geometry?
Well, let me say two things, okay? One is, how can this thing be knotted? It can only be knotted if this region here, this is a subsurface cross I that's embedded in this picture. It's kind of a nice exercise in the way annuli behave in free manifolds to show that the only way this could be knotted is if this thing is just a pi1 trivial disk, like a disk, or maybe a puncture disk sitting inside a surface. So if I can rule out disks, then I can show that this never happened. And I can rule out disks when I go back up here. I see if these objects are disk cross intervals up there, you can replace the disks by minimal disks, and you can control the way minimal disks intersect the solid tori. Because the solid tori have very, very short cores and very, very big radius, if I had a disk that was showing up in this picture, it would not be able to intersect the solid tori. Because if it did, its area would be too big. So it's a little bit of a long story. But if I had a disk, it does intersect the solid tori. Then when I turn it into a minimal disk, the minimal disk must not intersect the solid torus because there's not enough area in the minimal disk. And the point is that I intersected the solid tori minimally. So I can't lose an intersection in this way. So in fact, so you therefore argue that this case doesn't happen. That's what there's kind of a minimal repleted surface argument.
But minimally, you actually mean minimal.
Minimal area, or a ruled surface. Anything whose geometry you can control.
Could you draw the good pictures? I know they're a little boring, but...
The good pictures look like this.
And what about the horizontals?
Level torus.
Wait, the horizontal. So they're in here. Oh, I didn't finish the argument, right? The horizontal tori are floating in here, waiting for you to notice them. and I need to prove they're level tori, right?
They're, okay, not
So
but...
right? I need to prove that they're kind of level tori in this product structure. So what do? I look at this and I say, oh, once I have this picture, I find the following thing. So this came from SI, which was some huge surface running through this picture. But once I have this product structure, it follows that anything carried on B is going to be a fiber in SI for every I. For every I, I have the product structure, so if I take a fixed surface carried here, it's going to be a fiber in all of the manifolds. So then I apply the Tall's theorem. That's the end game, is to apply the Tall's theorem to this picture. Yeah.
Your theorem gives this subset of the curve complex of the fiber. Can you say anything about that? It's a finite set.
You mean the set of curves that
Yeah,
are...
exactly. Yeah.
It's a finite set. I think if you...
Finite set.
Yeah, it's a finite set. I mean, it doesn't say anything else about it.
Yeah.
Presumably, you can kind of pick whatever you want and use those for Dehn twisting. You'll get some bound on the big picture.
So is there a version of this theorem that doesn't say anything about Weil-Petersson, like just a three-manifold with some volumes and...
Sure.
So
I mean, that's kind of what's on the board. Yeah. Manifold. If you take a three-manifold with a torus boundary, and it has infinitely many Dehn fillings that are fibered, and all of them are in their infinitely many meridians on each component, then it has to look like this. So that's entirely a three-manifold state.
All right, that's okay.